We are Team Cyberdyne, and our project was to create a bug report classifier creation assistant. And yes, we are looking for ideas on a new name for that part, so if you have one, please see us at the presentation. I am Justin Canada. I am the testing lead and the data manager.
Marshall Brooks, and I'm the project manager and the back-end manager.
And I'm Hank Burton. I do the UI design as well as the documentation for our project.
Our client and advisor is our very own Dr. Emmett. And with that said, I will pass on to Marshall, who will give you the background of our project.
So, as of October 10th, 2012, the Firefox project received almost 800,000 bug reports, with averaging out to about 300 bug reports a day. This requires a triager, multiple triagers, someone who can determine the priority, the type, and assignment of a bug. As you can expect, bug triage takes both time and resources, such as which team does the bug belong to, which member of the team is best suited for a bug, and should that member of the team be unavailable due to vacation time or overloaded workload, who's the next best fit for that bug. So what we would like to do is use a assignment recommender to automate the process a little bit. So the problem is that recommenders are complicated and time-consuming to create. As you can see, what you'd have to do is you'd have to have a bug report repository set up and pull a selected number of bug reports from that repository. So you'd have to figure out which kind of bug reports that you'd take. You'd have to determine how many bug reports to take, how to label those bug reports, or which labels to use exactly, what you're going to use for features from those bug reports, and which algorithm you're going to use for creating your classifier. So our solution to this is to pull those bug reports from a Bugzilla repository using XML RPC. And we would save those bug reports in an XML format, client side, so that way it reduces a little bit of that network strain. And we would parse the data that we needed from those bug reports. From there, we'd be able to set a frequency cutoff, which means that if a certain developer hasn't solved, say, 5 bug reports, a bug report frequency cutoff of 5 would mean that that developer is not considered for future bug reports. Another thing that we would be implementing is something called heuristics. And that's our way of determining which labels we're going to use for each bug report. So for instance here we have a bug report in an XML format. And in the assigned to field we have Daniel Megger as the name. Now the problem is that Daniel may not have been the person who solved this bug report. It could have actually been the reporter, Eat Worko, because he determined that, say, he was better suited for the bug report in the end. Without heuristics, the classifier would just assume that Daniel Megger is actually the person who solved that bug report. So what we're going to do is we're going to display the statistics of our parsed bug report data, just so that way they could have a better idea of which configuration settings that they would want. We would train a classifier and create a recommender with that data. And then we would save that configuration of the completed recommender, so that way we could access it again at a later time. We would then also calculate out the accuracy of the recommender and display it for the user. So, precision and recall. How do we measure that accuracy? To do that, we would test the created recommender using a set of already solved bug reports. And what that would give us is a number of appropriate recommendations depending on how many correct recommendations it made against that solved set of bug reports. Using this number of appropriate recommendations, we could then determine our precision and recall. Precision being the number of appropriate recommendations divided by the number of total recommendations. And recall being the number of appropriate recommendations divided by possibly relevant developers, people that could have solved that bug report. And what we're using for that is how many people were on that component team. So next we're going to have Hank talking about what we have done so far, where we're going, and to give you a slight demonstration of what we have so far.
Alright, now that you guys have somewhat of an idea of kind of the project requirements, I can tell you, last time we presented, we were at a very limited interface. We had two windows. One was a main window that did nothing except for open a second window called the new recommender window, in which users could enter a bug report repository and pull some data. At the time, just one bug report. Where we are now, we are able to pull bugs from the repositories, and we are able to parse data from an XML representation of bug reports. You already saw a picture in a previous slide of what that XML data kind of looks like. While we parse, we remove developers based on the frequency cutoff, and that's done, parsing is done on both the testing and training sets. We use that data to train our classifier and test the classifier using the parsed testing set, and present some stats from the recommender training set, such as the number of classes, that's the number of developers, and the number of reports they solved. So for a demonstration of a project, I'm going to be demonstrating a few of those features. Alright, this is our user interface as it stands right now. First, we'll see the new recommender window. Here, the user can enter a repository. We have this default repository, and it's the one we'll be using for testing once we're pulling from the repository and parsing that data. Currently, we have data from the Eclipse bug repository, and that data is data that our client pulled for us. It's actual Eclipse bug data, and we're creating our recommender based on that. So to start with, we have our precision and recall variables here, just canned data. That's where we're eventually going to display the precision and recall of our recommenders as we create them. This status box shows in real time what's happening with our recommender creation. And here we have our frequency cutoff page. I'm going to go ahead and create a recommender with 0 frequency cutoff. And you can see we've already parsed all the reports. It takes very little time currently, though that's going to go up as we have more reports and more words in the reports to parse. We've completely trained our classifier after 11 seconds, and then we queried it, asked it from our testing set, who do you recommend to fix each of the reports in our testing set? And that was this window that popped up. Each report ID has a developer assigned to fix that report. We can look here at our recommender set. We have this occurred to cutoff at 388.615. To kind of demonstrate the frequency cutoff here, we're going to remove occurred to cutoff from that by setting a frequency cutoff higher than 15. So I'm just going to go for 30. It's going to greatly reduce the number of classes. It's going to reduce the amount of time it takes for a recommender to train. As you can see, that 11 seconds for training the classifier has been reduced all the way down to 1 second. And we've still queried it for every single bug report. As you can see, this was the old recommendations. Occurred to cutoff is no longer in there. Selenium Quartet has replaced him for that particular bug ID, as is the case with several other bugs throughout our recommended set. Here you can see again who's left in that classifier set. And this graph is dynamic. Whenever I change that, it'll change the graph. We have every developer associated with an ID and the number of reports that each developer remaining has solved. So at the top we have Selenium Quartet with his 87 reports here. And to kind of give you an idea of why we need heuristics, this platform UI triage, that is not a username. It's not somebody who's solving reports, not a developer. So we need to have some way of assigning the reports that are being parsed under that name to somebody. We need to find an assignee within those reports. This heuristics page is ultimately going to be where a user can do that. That concludes our demonstration. And I'm just going to conclude here my section with where we're going after this is we have 2 more iterations. Our next iteration is going to be all about pulling from the repository and saving to an XML format. Again, the pulling from the repository is mostly done. We just need to save to an XML format that our parser takes. We need to save the recommender configurations after we've created a recommender, implement the heuristics, and then calculate the precision and recall of the data from that recommender. And then our final iteration is going to be about collecting user statistics and polishing the UI up, assuming, of course, that we have several bugs at that stage. We allotted a lot of time in the final stage for that. To give you an idea about collecting user statistics, there's some questions that we want answered. This is a research tool, and so some of them, how many classifiers does a user want to create before they're satisfied? Can we make this process of recommender creation simple enough that it doesn't take 100 different recommenders or different classifiers for them to come up with a satisfactory recommender? What precision and recall values are satisfactory for our users? What frequency cutoff do users choose for each classifier? What heuristics are being created? And are there any common heuristics, something that we could incorporate into the machine as opposed to having the user set them at runtime? And then how long does it take? How many different iterations of creating a classifier does it take the user to create optimal heuristics for their project? And I'm going to hand it over to Justin here to talk about our testing.
All right, to finish off here, I'm just going to go briefly over our testing. So system testing is our main form of testing. All our components, such as our classifier and our XML parser, are tested individually before they are put together in the UI. So we do test, make sure our parser is working correctly and our classifier is doing what it's supposed to do before we feed in our parse data into the classifier. We also run our project on multiple machines to make sure it works. We find that it runs a lot better on machines with more cores than them. So for our other testing methods, we do have weekly and bi-weekly meetings with our client advisor. It's really helpful for us to get this really quick feedback. That's probably what's made our UI the way it is right now. We also chose to use Visual Studio's built-in test projects as opposed to external plugins. We did this for a number of reasons. One of them is that it comes with a lot of nice built-in features, such as code coverage and branch testing natively. That was really convenient for us. We also do a lot of smoke testing just to make sure that the thing runs when we want it to. When we add new features and stuff, we want to make sure that it just works off the bat. We also do unit tests with image components, like I said before. And to compare our results to the correct ones that Dr. Anda gave us, all we do is go down the list one by one by the bug IDs and make sure that our recommendations are the same as Dr. Anda's. And if they don't match, we just give a percentage of how well we're doing, and that's how we keep track of how well our classifier is doing. And with that, we will open the floor to any questions you might have. Yes?
I missed the point. So you talk about multiple classifiers. Can you give examples of the classifiers that you combine?
Okay, so at the moment we're just using one classifier for the entirety of the program. One thing that we may implement in the future is a classifier for each component, but that's just a down the road sort of thing. But for the most part, we're just using one classifier for all this.
Okay, what it is?
What is the classifier?
Yeah.
We're using a support vector machine for our classifier.
Okay, then I have a question.
Of course, the support vector machine is a popular one, but how does it fit to your type of data? Do you have a homogeneous data? Because support vector machine requires that all data are homogeneous.
Yes. When we parse the data, we create a bag of words object, and that is an array of double values. So we iterate over each bug report and increment this table essentially at the indices of every word. So ultimately it looks like a table of a bunch of 1s, 10s, 0s, 5s, etc. But the machine reads that and then checks each report and classifies it. And we also have an outputs array which checks the assign to field and each developer corresponds to an indice of that table. So when we have a report, we say that the word user interface is in that report 10 times. And the guy who works on user interface stuff is marked with a flag, a 1, if you will, in the integer set. So the two correspond to each other, and we feed that into the machine, and then later on the machine outputs from a new bug report an array that looks exactly like the integer array, and the indice in that array that's greater than 0 is our developer who should solve that report. I don't know if that quite answers your question.
Of course, I don't know exactly how you data organize it, but I'm guessing that, say, there is a bug report, and then you get some characteristics from that bug report. Say, you recognize that this bug, say, 70% of the user interface and, say, 30% of, say, internal ROM computation.
Mm-hmm.
Yes.
Yes.
Okay, so you have a different type of characteristics, basically internal computation and, say, user interface.
Mm-hmm.
These are two different modalities. So even if you express this in the numbers, but in essence, you are talking about different modalities. So when you talk about the same modalities, where support vector machine is a good method, it would be, say, a typical example, you have a stock market, and you have a first parameter, stock today, stock tomorrow, stock 3 days. So all of these are about exactly the same physical, about the price of the stock. In your case, it's a different thing. So I'm asking, I'm not objecting this, but it means that you need to be very accurate to be sure that support vector machine is the right one.
Yeah. What we're doing is, while we parse all of the bug reports we have pulled, we make a single list which contains each unique word that's come across throughout all of those bug reports. And then as we go through the bug reports again, we just tally up how many of those words we come across in individual bug reports. And we found that in bug reports of different components, different vocabulary is used. So it ends up segregating each developer's component team into component teams for the bug reports themselves. So it does end up giving that kind of separated modality that you're talking about.
Okay. So I think your question is, why are they using support vector machines and not something else?
Yeah.
Right? And the reason is because the research literature has pointed that is the accepted approach, or accepted algorithm to use for this particular application. So they're not choosing it. They were basically told that's the thing to use.
I have no objection again.
Yeah.
Especially having
And
my friend, I cannot say.
What I'm saying is the details of why you're selecting that is actually outside this project.
No, I just telling that depends how they organize data. It can
Yes.
be perfect method and it can be very wrong method.
Okay.
That was I'm telling.
Okay. I hear it. I see.
Okay, so how do you choose the two parameters of the kernel of the support vector machine?
That's, I'm afraid I'm not quite understanding
Okay,
your question.
so
How do
support vector machine has essentially two parameters that have to be optimized.
Mhm.
How do you optimize them?
Well, one way that we optimize the inputs of our features is by filtering out just all the stop words, so that way we don't have words of no consequence such as and or the. Another thing that we're doing is we're using, or we're going to be implementing TF-IDF, and Justin knows a little bit more about that.
Yes, TF-IDF is term frequency and intra-document frequency. And term frequency is, for example, if the word like window comes up a bunch of times, we can assume that the word window is very important and that bug reports with the word window in them should be treated as such. And then we kind of weight our inputs based upon that. And then intra-document frequency is is per bug report. If the word window appears multiple times in a bug report, we can assume that that is more important than the rest, and we weight that differently.
Yeah, I'm sorry to interrupt. I think my question was not very clear. So when you start using a support vector machine, you actually use a family of vector machines, or support vector machines, based on the parameters, yes. How do you choose the parameters when you use them?
So what was the kernel function we used?
Quadratic.
The quadratic.
Yeah, the
Well,
quadratic.
what criteria do you use it, or how do you do that exactly?
Not sure we follow exactly.
We have
Again, that was from the literature. That was the particular kernel that would be used for this application. They
So
did-
you use this like there were preset.
Yes.
Okay, so the next idea here is to optimize it yourself. Yes. There is a standard technique for doing this using a very simple trial and error technique. And you use a validation test and perhaps a cross-validation if possible. And you find this. You don't need to rely because depending on the data you have, these two parameters can vary, they can be different, and the results are very, very different from this. So try perhaps, I don't know how much time you have, but you don't possibly have the background right now to do this, but try to optimize them yourself. That's the idea.
Okay. Can do. Any other questions? Okay, thank you very much.
Thank you.